Welcome back to our Chem 152 video series. In this video, we'll study precipitation and how it can depend on pH for certain compounds. The compounds we're looking at in this problem are MgOH2 and PbOH2. We begin with a solution that has both magnesium and lead in it, and we are asked at which pH will each compound begin to precipitate. Now, you may recall from a previous video that if QSP is greater than or equal to KSP, you'll begin precipitating. Therefore, what we'll need to do is write an expression for QSP for each compound and then set it equal to KSP. Let's try that, starting with MgOH2. If MgOH2 breaks into pieces, it will break into Mg2 positive and 2 pieces of OH negative. We can write a QSP expression and say that QSP will be Mg2 positive multiplied by OH negative raised to the second power because we have a 2 in front of the OH. We'll set this equal to the KSP, which for MgOH2 is 1.8 times 10 to the negative 11th. Now, we already know what magnesium 2 plus's concentration is because we are given that it is 0.01 molarity. So we'll say 0.01 times OH squared is equal to 1.8 times 10 to the negative 11th. We divide both sides by 0.01, and we'll end up with OH squared is equal to 1.8 times 10 to the negative 9th power. Now we can take the square root of both sides, and this will give us our OH concentration. If we put this in a calculator, we end up with 4.24 times 10 to the negative 5th power. Based on that, we can find our pH. Now pH can either be negative log of H3O, or you can write that pH equals 14 plus log of OH. Since OHs are known, we can place that in these parentheses in the second form of the equation, and we'll say pH is equal to 14 plus log of 4.24 e negative 5th. If we place this in a calculator, we'll end up with a pH of 9.63. Therefore, the moment we adjust the pH up to 9.63, we'll begin precipitating magnesium hydroxide. All we would need to do is start with pure water and add a small amount of base to it, and then the MgOH2 will begin to precipitate. Now we'll run the same calculation on PbOH2. We can begin by writing an equation for PbOH2. PbOH2 will break into lead 2 plus and 2 pieces of OH minus. We already know that our lead concentration will be 0.01 molarity, and our OH is unknown. And we'll write a KSP equation for this. We'll say KSP is equal to 1.2 times 10 to the negative 15th. Set this equal to the lead concentration, 0.01, multiplied by OH raised to the second power, again because of the 2 in front of the OH. We divide both sides by 0.01, and we'll end up with 1.2 times 10 to the negative 13th is equal to OH squared. We'll take the square root of both sides. We'll end up with an OH concentration of 3.46 times 10 to the negative 7th molarity. Once again, we can go to our pH equation and say pH equals 14 plus log of my OH concentration. We'll have 14 plus log of 3.46 times 10 to the negative 7th. If we place this in a calculator, we'll end up with 7.54 for my pH. Let's compare this pH to the pH from our first problem. Neutral pure water will have a pH of 7. And we just found that we'll begin to precipitate at a pH of 7.54, which is only slightly more basic than pure water. At that pH, we'll precipitate lead hydroxide. If we adjust the pH further to 9.63, we'll begin precipitating magnesium hydroxide as well. It turns out that if we have this mixture of magnesium and lead, we can adjust the pH to somewhere within this window between 7.54 and 9.63. For example, if we adjusted the pH to something like 9.5, this would precipitate the lead, but leave the magnesium alone. Therefore, if you did have this combined solution and you wanted to separate the metals, we could just adjust the pH to 9.5 or really anything slightly below 9.63 to get optimal separation of the metals. Thank you for watching, and we'll see you again soon.